Hello, dear friends. How are you?
Hello, Doctor.
Hello.
Good morning.
Morning, how are you?
Thank you so much.
I hope you are fine.
Thank you. Thank you, dear friend. Also, I hope you are all well and be ready for our today's class. If you have any question, you can ask in the beginning of our class. But if you do not have any question, I can start my lecture in the rest of your topics from the previous session. Okay, there is no question. In the previous two sessions, we talked about what is an ODE, what is an initial value problem related to an ODE. Also, we talked about what is the numerical solution of an specified initial value problem for an ODE. We saw that for the problem in this form, with this first order ODE subject to this initial condition, we want to obtain a sequence of approximations called y1 to yn at the time points t1 to tn for approximating unknown solution y of this problem at these points in this form. So we want to approximate y at these discrete points tn. Y is our unknown solution of this problem, and y1 to yn will be approximations of this unknown solution at these discrete points. In the previous session, I talked about the famous Picard's theorem. Picard's theorem, we saw that the Picard's theorem. Picard's theorem is about the unique solvability of our initial value problem. Here we saw some assumptions for right hand side function f and the other details of our problem. To obtaining this result, there exists a unique continuously differentiable function yx defined on this domain, which satisfies the ODE1 subject to initial condition 2. Here we called this condition a Lipschitz condition. Here L is our Lipschitz constant. Also, we talked about the general sketch of the proof of this theorem without considering the details. We discussed about this proof, and we defined y not of x, our initial value of our problem, and we define this recursive relation, and we mentioned that in Picard's in the proof of Picard's theorem, we will prove that this recursive the elements of the sequence and the elements of the sequence generated by this recursive relation will converge to this function, and this will be our unique solution of problem 1 and 2. Also, in the previous session, we worked on some examples about related to this theorem, and based on this proof, we introduced our first numerical methods in this course called Picard iteration. In Picard iteration, we saw that by considering phi naught equals y naught, or initial value in our problem, and generating phi I by this recursive relation, then we will have a sequence of approximation for our problem. Also, we presented some examples for Picard's iteration. Here in this problem, y prime equals y subject to y at 0 equals 1. We have phi 0 equals 1 plus this integral based on this relation. Also, we can obtain phi 1 based on the values of phi 0 and this recursive relation. Here we have phi 0, we can obtain phi 1. Again, by substituting phi 1 in the right hand side, we can obtain phi 2, and continuing this process will result phi n in this form. So again, we can saw that phi n plus 1 can obtain from phi n and will be in this form. So finally, we can result when n goes infinity, the limit of this sequence will be in this form. So based on the details of Picard iteration, the limit of this sequence or phi of t equals e to the t will be the solution of our initial value problem y prime equals y subject to y0 equals. So by using Picard's iteration, we found the exact solution of this problem. Also, as another example, we have this equation subject to this initial condition. Again, based on the algorithm of Picard's iteration, we can obtain yk plus 1 subject to yk. Subject to y0, we can obtain y1. Subject to y1, we can obtain y2. And continuing this process will result y3, y4, and so on. If someone consider, for example, 5 iteration of Picard's theorem, we will have an approximation. So another one, continuing this process for 10 terms, then y10 will be a better approximation. The number of iterations will be based on the accuracy we want to obtain in our numerical example. So, for example, in your exams, we will want you to continue this process, for example, for 7 terms or 10 terms. So, you must continue this process by using y3 to obtain y4. For example, I want you in your midterm exam, please find y5 based on Picard iteration to approximate the unknown solution of this problem. So you must obtain y1 from y0, y2 from y1, y3 from y2, and continue this process to obtain y4. Then y4 will be obtained from y3, and finally you must obtain y5 based on y4. This will be the solution of our question. So in your exam, we will specify the number of iterations, and you must continue this algorithm to obtain this desired approximation. Okay, those were the topics of our previous session. Now, in this session, I want to, at the first part, I want to explain Picard's theorem for an initial value problem related to a system of differential equations. In the previous version of Picard's theorem, we considered some assumptions on an ODE subject to one initial condition. Here we want to extend our previously studied Picard theorem for a system of m differential equation in this form. Here we have y prime equals f. Here we have y and f in this vector form. Here in this equation, y is an unknown vector and f will be an m-dimensional vector, or m-dimensional function will be a vector of functions. Each row of this vector will be an m variables function, m plus 1 variables. Here f1 will have the variables x, y1 up to ym. Similarly, f2, f3 to fm will be a function of m plus 1 variables. Here we have the first order derivative y prime defined dy subject to dx. X is our independent variable. This is a single variable, is our independent variable in our problem. For this vector equation y prime equals f of x and y. We have this initial condition. Y at 0 equals y naught equals this vector y1 0 up to ym 0. So here we have a vector or ordinary differential equation subject to this vector of initial values. We want to solve this problem. Y prime equals f of x and y subject to y at x not equals y naught. Here y naught is in Rm, Euclidean space, M order of Euclidean space. F will be a function from the domain x0 to xm for variable x, and Rm for dependent variable y to Rm. Rm will be M order Euclidean space. Here we will introduce this Euclidean norm for any M order vector V in Rm, defined based on the elements of this vector. In the other words, here V will be this vector V1 to Vm. This will be our vector. For this vector, the Euclidean norm will be defined by this relation. Okay, we want to focus on this system of M differential equations subject to this initial condition with this Euclidean norm. Picard's theorem for this vector initial value problem will be similar to Picard's the main Picard's theorem. But here our problem is in vector form, so some details will be changed. Suppose that f is a continuous function of its arguments x or vector y in a region u of this variable. This region will be a subset of Rm plus 1 and this domain will be this parallel piped domain R, x and y when x is between x0 to xm, and the values y will satisfy this relation. And the norm of y minus y naught will be less than or equal to capital Ym. Here xm is a value greater than x naught, and ym will be a positive constant. Also, suppose there exists a positive constant L such that we have this relation. This relation is a Lipschitz condition for function for vector function f. and we will have this condition on our domain parallel piped domain R for any x and y and x and z in the domain R. Finally, let m is the maximum value of norm of function f on the domain R, such that m times x m minus x0 is less than or equal to 1. Now, our hypotheses are complete, and this is the result of this extended Picard theorem. There exists a unique continuously differential function y defined on the closed interval x0 to xm, which satisfies the problem 5 in this form. So here we have this extended theorem based on this hypothesis. We will resolve the unique solvability of our vector form initial value problem related to ODEs. This is important. This is an important theorem in the field of vector form initial value problems for a vector of for a system of differential equation. In the other words, if we have a system of m ordinary differential equations subject to a vector of initial values, then this theorem will guarantee the unique solvability of this system. So this theorem is very important in the field of systems of ordinary differential equation. Okay, up to now, do you have any question, dear friends? Everything is okay? Do you have my voice? All of you are connected to the class? Mr. Sharif, Mr. Abdullah, Mr. Ashar, Mr. Al-Khafaji.
Thank you, Doctor. No have question.
Okay. After this extension of Picard's theorem, now I want to define another concept in the field of ODEs. This is stability. First, I want to define this concept at definition 1. A solution y to the problem 5, this ODE subject to this initial condition, will be stable on this domain if we have for every value of epsilon, every positive value of epsilon, there exists a positive value delta such that for all vectors z satisfying in this relation, norm of v at x naught minus z is less than delta, the solution W to this initial value problem y prime equals f of x and y, satisfying in this initial condition, we define for all x in x0 and xm and satisfied in this condition. Let me repeat this definition. Here we have two problems. First problem is this problem. Y prime equals f of x and y, subject to this initial condition. Now, in this definition, we define a new problem. Y prime, y prime equals f of x and y subject to this initial condition, y at x naught equals z. Here we have two problems. The first problem is problem number 5. The second problem is this perturbed problem. Here we have a change in our initial condition. The initial value will be z instead of y naught. Also, we have this assumption. If y, the solution of this problem, be the function v of x, then v at x naught minus z will be less than delta. In the other words, y0 minus z will be less than delta. Delta is an small value. Now we will notate the solution of this problem. Y is equal to v of x and the solution of this problem be y equals w of x. This is the solution of this problem. This is the solution of this problem. Here we have a small change in our initial value satisfying in this relation. Y naught minus 0 or v of x 0 minus z will be less than delta. Now, based on this definition, we can result this small change in our initial condition will result this change in our final solution. If y naught minus z be less than delta, then the obtained solution of this problem will change subject to this condition. Here both of the values delta and epsilon will be some small values. In the other words, based on this definition, if we have some small changes in our initial condition, will result a small change in our solution. In this situation, we will say our problem is stable. In the other words, the solution of our problem will have a stability condition. So a solution is stable on this domain x not to infinity, then we will have a very strong condition, and we will say that our solution is stable in the sense of Lyapunov. Also, as our final part of this definition, if we have the limit of the norm of Vx minus Wx tends to 0 when x goes to infinity, then our solution we will call asymptotically stable. This is the definition of stability, and based on this definition, the concept of stability can be expressed in this form. If we make a small change in the initial data, which includes both in differential equation or in our initial value. So if we have any changes, any small changes in our problem, if these small changes in the data lead to large changes in the solution, then we say our initial value is unstable or ill-conditioned. Whereas if we have small changes in the data and these changes lead to small changes in the solution, we will call our problem stable or well-conditioned. So here we have two main concepts. The problem is stable. The problem is stable or unstable, or our problem is ill-conditioned or well-conditioned. These two concepts will be related to our definition. If a small change in the data of our problem, the known data of our problem, causes small changes in the solution, our problem will be well conditioned and will be stable. If small changes in the data lead to large changes in the solution, then we have some small changes in the problem, but it results large and meaningful changes in our final solution. So our problem will be in condition or unstable. Okay. Now let me consider some examples to clear this new concept. At the first example, for more illustration, let me consider this problem. Y prime equals 100 times y minus 101 times e to the minus x, subject to initial value y at 0 equals 1. Here we have a solution y of x equals e to the minus x. In this initial value problem, our solution is known. We know the solution of this problem because this is just an example. We want to explain the details of stability subject to this problem with the known solution. Here, let me change some negligible value to the initial condition of our problem, from y0 equals 1 to y0 equals 1 plus epsilon. Here epsilon is a small number, and here we have two different problems. In both of these problems, the equation is the same, but we have some changes in our initial conditions. Here we have y0 equals 1, but here we have y0 equals 1 plus epsilon. So the only difference between these two problems will be at our initial condition. You can see by substituting, this is the solution of this problem, and here you can see with simple computation, this is the solution of this problem. So we have a solution for this perturbed problem in this form. You can check it by substituting. You can replace y epsilon in both sides of this equation. You can see this is the solution of this problem. Also, when x equals 0, you can see it will be 1, and from it we will obtain epsilon. So y epsilon will be 1 plus epsilon. So we have this solution for this problem, this solution for this perturbed problem. Now, if we obtain the difference between y epsilon and y, you can see this difference will be epsilon times e to the 100x. Now, if you increase the value of x to infinity, this difference in this exponential form will go to infinity. When x goes to infinity, epsilon times e to the 100x will go to infinity. So y epsilon minus y increases very rapidly when x increases to infinity. So from this definition, this difference will not go to 0. So in this case, when x goes to infinity, let me write in this form, limits of y epsilon minus y normal, y epsilon minus y goes to infinity when x tends to infinity. Here, the limit of this norm will not go to 0. So, our problem will be unstable. In the other words, problem will be an ill condition problem. This is an example of unstability. This is an example of unstability. Now, let me consider another example. Consider this problem, y prime equals minus y plus 1. Here, our domain for the independent variable t will be 0 to b, subject to initial condition y not equals 1, y at 0 equals 1. This is our main problem. This problem you can see easily. This problem have the solution y at y of t equals 1. Now let me perturb this problem. We will change this initial condition from 1 to 1 plus epsilon. With this change, we have a new problem. Y epsilon prime equals minus y epsilon plus 1. Subject to this initial condition, y epsilon at 0 equals 1 plus epsilon. You can see easily the solution of this new problem will be this function, 1 plus epsilon times e to the minus t. Now, let me consider the difference between the solution of this perturbed problem and the solution of our main problem. Y minus y epsilon will be minus epsilon times e to the minus t. Now, the norm or the absolute value of yt minus y epsilon, this difference will be the absolute value of this function, and you can see because here we have the exponential of minus t, this will be less than epsilon. Now you can see limits of y minus y epsilon limit of this. Here you have this relation. This absolute value will be greater than 0 and will be less than epsilon. When epsilon goes to 0, from this, the famous sandwich theorem, you can result the absolute of y minus y epsilon will go to 0. So this problem will be stable. A small change in our data, in our initial value, will cause some small changes in our solution. So our problem will be stable or well conditioned. So here we saw that two different examples. At the first example, our problem was ill conditioned, and in the second example, our problem was well conditioned, because in the first example, small changes in our initial condition results large changes in our solution. But in the second example, small changes in the initial condition result small changes in our solution. So our problem is well conditioned. Now let me or tell example. Here we have this problem. Y prime equals lambda times y of t minus 1. Subject to this initial condition, y at 0 equals 1. Here again, you can check easily. The solution of this problem will be y of t equals 1. Now we want to perturb our problem by changing the initial condition from 1 to 1 plus epsilon. Now this new problem will have this solution. Y epsilon equals 1 plus epsilon times e to the lambda t. The difference between the solution of this problem and the solution of this perturbed problem will be this value, minus epsilon times e to the lambda t. Here for this difference, the absolute value of y minus y epsilon based on this definition will be the absolute value of epsilon if we have lambda less than 0 will be epsilon e lambda b. B is the end point of our domain in our problem, the domain of our problem. Then in the case lambda is less than 0, the upper bound for this difference, the absolute value of this difference will be epsilon, the absolute of epsilon, the absolute value of epsilon. In the case lambda is greater than 0, then this maximum will be absolute value of epsilon times e to the lambda b. Now we have two different situations. We have two cases. At the first case, when lambda is less than 0, you can see when epsilon goes to 0, y, the absolute of y minus y epsilon will decrease. Okay, so in the case lambda is less than 0, when t goes to infinity, this difference will go to 0. So our problem in the case lambda is less than 0 will be well conditioned, and the solution will be stable. In contrast, when lambda is greater than 0, this value, this error value, the absolute of y minus y epsilon, will increase when t increases. In other words, for example, when lambda b is a small value, a large value, for example, greater than 10, the change in y is quite sign efficient at t equals b. So our problem will be increasingly unstable and increasingly ill-conditioned. So you can see in this third example the stability or unstability. In the other words, the well-posedness or ill-posedness of our problem is related to this confusion. In this problem, with this initial condition, our problem can be well conditioned or ill conditioned based on the values of lambda. For example, if we have this problem, y prime equals minus, for example, minus 2 y minus 1. Here lambda is minus 2. In this problem, subject to this initial condition, will be a well-posed problem. The solution will be stable. But if someone change the minus 2 to plus 2, then this problem will be ill-conditioned. So in this problem, in this initial value problem, the well-posedness or ill-posedness is related to the coefficient lambda. Okay. Is there any question?
Thank you, Doctor. No, I have a question.
Very good. Here we are familiar with a new concept, well-posedness. We have, if we have some small changes in our initial condition or in the data in our ODE, if we have this condition for between the solution of our main problem and or the solution of our perturbed problem in this form, we will say our problem is well posed and the solution is stable. Here we can have another theorem. In this theorem, we will say if or for this problem y prime equals f of t and y subject to this initial condition y at t0 equals y0 or y not. If in this problem, if the right hand side function f satisfies a Lipschitz condition, then this problem will be well posed and the solution will be stable. This is a very interesting theorem. In this theorem, we have just this hypothesis: a Lipschitz condition for our initial for our right hand side function in our ODE. If we have Lipschitz condition for function f, then our problem will be definitely well posed. So, if you have an initial value problem, you need just check the right hand side function f to prove this problem is stable. So here in this theorem we will have a condition for well-posedness of a problem. You can check this condition if our right hand side function f have Lipschitz condition, then our problem y prime equals f of t and y will be subject to the initial condition y at is not equals y not will be stable, but or will be well posed. But if we do not have this condition, then maybe our problem is well posed or ill posed. But this theorem just will be used to check well-posedness. If we have the Lipschitz condition, definitely our problem will be well-posed. In contrast, if we do not have this condition, then we must to check maybe our problem is well-posed or ill-posed. This theorem is just for checking well-posedness. Okay, these are our contents for the concept stability. We are defined in this session. Now let me upload another file about the second chapter of our course. At the first chapter, we explained some preliminaries, some basic definitions related to ODEs, related to initial value problems of this equation. We talked about initial conditions, boundary conditions, the order of our equation. Also, in the previous session, we talked about the famous Picard's theorem for unique solvability of our initial value problems. In today's class, we worked on we worked on an extension of Picard's theorem for a system. Also, we introduced the concept stability and well-posedness or ill-posedness of initial value problem. All of these concepts were related to basic definitions and the basic definitions of ordinary differential. So all of you are familiar with ODEs, about initial values of ODEs. Also, you are familiar with the concept numerical solution of an ODE. Also, we are familiar with our first technique to obtain approximate solution for these types of problems. This first technique is the Picard iteration, and now we want to continue our discussion, and we want to focus on one-step methods. This will be the second chapter of our course. The main reference of this chapter will be Atkinson's book, and in this chapter we want to work on one-step methods, and the main introduced method in this chapter will be the famous Euler's method. The Euler's method will be the first numerical technique in this course. In this technique, we will obtain some approximations for our unknown problem. Now, I want to present a general sketch of this method, and in the next session we will focus on the details of this method. Again, we want to obtain numerical solution of this problem, y prime equals f of t and y, subject to this initial condition. Again, we will choose this discrete set of points t1 to tn between t0 and b, the domain of our problem. For simplicity, we will choose this set of points in equally spaced points. In the other words, here each discrete points Tn will be defined based on this definition. So the space between these points will be equal. We will try to present a recursive relation to generate some approximations yn for the unknown solution y at point Cn. In the other words, y at Tn will be approximated with yh at Tn. And for simplicity, we will show YH at Tn with Yn. So YH generated by our numerical technique, for example Euler's method, will be an approximation of our unknown solution Y at a set of discrete points Tn, T1 to Tn. In details, in the next session, we will see by using this relation and substituting in our main equation, we will have this relation. Now, neglecting this approximating notation with equal notation, we will obtain this relation. Here we will see if we choose y0 equals capital Y, not or initial condition, initial value, you can obtain y1 from this relation by substituting n equals 0 and substituting t0 and y0 in the right hand side. You can obtain y1 again by substituting n equals 1 and substituting y1 and t1 in the right hand side. You can obtain y2 and you can continuing this process to obtain y3 up to yn. So this will be a numerical technique. You have a recursive relation and you can obtain some approximation. This is a general sketch of our first numerical technique, Euler's method. I will present more details about this technique inshallah in the next session at Wednesday. So it's enough for our today's class, and we can continue our discussions in the next session. If you have any question, I'm ready to answer your friends.
Okay, Doctor, now I have a question. Thank you.